Erlang is a programming language with primitives that help software engineers build distributed systems. When a process is malfunctioning in Erlang, the philosophy of the language is to let the process crash. And in a distributed system where unexpected faults happen on a regular basis, this philosophy of let it crash simplifies how we reason about an Erlang system. Other distributed systems advantages of Erlang include the garbage collection strategy. Every process in Erlang has its own garbage collector, which means it's easier to construct systems without a stop-the-world garbage collection process like you can have with the JVM. Francesco Cesarini is the founder of Erlang Solutions, and he joins the show today to discuss the book that he wrote with Steve Vinoski. The book is called Designing for Scalability with Erlang and OTP. It's a great read. I recommend you to check it out. Thanks for listening to this show. If you enjoy it, please share the show on Twitter or Facebook. Tell your friends if you think they would be interested in it. That translates directly to growth and revenue for this show. And as the revenues grow, I will reinvest the money into Software Engineering Daily. You can help keep this flywheel spinning. You can help keep the show growing and allowing me to produce new types of content and new mediums, which I would love to do. And you can help that by sharing with your friends and helping us grow. So thanks for listening, and now let's get on with this episode. Software engineers never stop learning. If you are listening to Software Engineering Daily right now, you enjoy learning so much that you listen to a podcast about technical software topics. IT Pro TV has videos for people like us, people who never stop learning. I'm using IT Pro TV right now to learn about Amazon Web Services, and I found 10 hours of high-quality videos about EC2, elastic load balancers, orchestration, cost management. If I ever decide to start my own tech company, I will need to know how to manage the cost of my servers. Go to itpro.tv/sedaily to get started with a free 7-day trial of videos. You can then use the promo code SEDaily and get a 30% discount, and that discount is permanent. Watching these videos, I have learned how to configure auto-scaling groups together with load balancers. I've learned how to configure a database that can scale up without inconsistencies. If I wanted to test out of the Amazon SysOps certification right now, I could. There are also courses about Microsoft operating systems and networking, VMware virtualization, Cisco routing. You can watch 70 hours about Cisco routing and switching, and it is engaging and entertaining material. If you listen to Software Engineering Daily all the time, this is the kind of material that you will love. You can put it on in the background, and you will find yourself just absorbing the information without even realizing it. You can try it free for 7 days. Go to itpro.tv/sedaily. Use the promo code SEDaily to get 30% off, and after you try it free for 7 days, I have no doubt that you will want to continue to invest in yourself and your future. Thanks to IT Pro TV for sponsoring Software Engineering Daily and for producing this top quality content. Francesco Cesarini is the author of Designing for Scalability with Erlang and OTP. He wrote the book with Steve Vinoski. This is a book about building robust and fault-tolerant distributed systems. Francesco, welcome to Software Engineering Daily.
Thank you for having me.
So we've done some shows on the basics of Erlang, and I want to spend most of our discussion on some of the usage patterns and strategies of some modern, perhaps advanced Erlang usage. But to put things in historical context, Erlang was created back in the 1980s when Ericsson was developing the next generation of telecommunication systems. And telecom turned out to be a problem domain that was somewhat similar to the systems that we build today as software engineers. What was it about the 1980s telecom industry that was the point of creation for such a powerful distributed systems language?
So if you go back to the late 80s, there were two things which were happening in the whole telecom market. First of all, they were rolling out the first generation of digital switches. So all of a sudden, your phone calls weren't being switched by connecting copper wires from end to end. You actually had computers routing your calls and setting them up. The second thing which was happening was the deregulation of telecom markets. So all of the ministries of post and telecommunications were losing the monopolies over providing telephony services. And something similar was happening in the US, where Bell was split up into a lot of baby Bells. And so what this meant for telecom providers is that time to market became critical, but at the same time time to market had to be critical without sacrificing the reliability, availability, and scalability of the telecom systems. Back in the 80s, telecom systems were the only way of connecting people, and so those networks had to scale and they could never go down. It was actually, there were huge penalties if telecom networks went down. You'd be shamed on the front pages of the papers the following day. And it was also regulated by law. The law stated that your telecom network had to work even if there were natural catastrophes happening, because you had to be able to dial 911. So you made sure that your systems were robust and could handle the load they were designed to carry.
So the telecom industry had lots of connections, lots of high throughput systems, and the probability of faults were high. And yet these systems had to be fault tolerant, which is a term that gets thrown around very often in the discussion of distributed systems, especially today. What are some examples of modern faults? Like, what is a fault, and how should we be tolerating a fault in a modern programming environment?
So, there are many, many ways. Your question is a very hard one in that there is no one size fits all. And that's actually something I realized when you're writing designing for scalability. The first question I ask myself is, why isn't there a platform which, will give us, scalability and reliability out of the box? And the reason is that, everything consists of a set of compromises you've got to make. And the design choices will go in and actually create these compromises for you and these trade-offs. So going back to your question, what is fault tolerance? Well, fault tolerance means often, no single point of failure. And if you look at an end-to-end system, what could fail? It could be the network failing. It could be a process in your node failing, so an actor. It could be the whole node failing. It could be a computer failing. It could be a bug, so your software starts malfunctioning. So it could be a power supply. It could be a network administrator tripping over the cable. So there are a lot of things which can go wrong. And when designing your software, you need to start keeping in mind, what level of fault tolerance do you need? You actually need redundant power supplies. Mm-hmm. Or, do you need redundant data centers?
Well, and so we also, we need fault tolerance at the level of servers and databases. And, we have these in the form of replication and load balancers. Regardless of the language that our system is written in, we can have fault tolerance either through software or through hardware layers. So, but Erlang gives us fault tolerance at the language level. Why is that important? Why do we need fault tolerance at the language level?
So the way it works with Erlang, so what you say is completely correct. You can achieve fault tolerance and scalability with any programming language. What Erlang gives you is particular semantics in language and the virtual machine, which removes a lot of the accidental difficulties you'll have when creating fault tolerant systems. So it's got, built into the semantics, it's got mechanisms to monitor your processes, to monitor remote nodes. And it will automatically detect if something's gone wrong and be able to react on it. So if you notice that a process managing a phone call has, terminated abnormally or in fact crashed, in a generic way, you decide how to handle that particular crash or termination. And this generic way could be a very similar way to how you would handle a WhatsApp message crashing or an action in a massively multi-user online game.
Right. And so we'll talk about the principles of Erlang in more detail. I'd like to get into OTP. OTP is this set of frameworks and principles and patterns that help guide how to structure Erlang systems. And our discussion of this, I'm sure, will touch on core components of the Erlang language, but also touches on the kind of abstractions and the things that are built around Erlang. And this includes the Erlang runtime system, the kernel, the standard libraries, the system application support libraries. What are some of the important tools that OTP makes available?
So before answering that particular question, I'd like to go into, well, OTP consists of three things. It consists of the Erlang language, and by that we mean the semantics of the language. It means the virtual machine. You can copy the libraries, but if they don't run on the Erlang virtual machine, in this case the Beam emulator, you can't copy the semantics. And thirdly, a set of design principles. And I think, the book focuses on the design principles. And what OTP tells you is how do you actually go in and architect a system to run on a single node? And then how do you go in and connect all of these nodes together to give you a complete end-to-end system, which might offer a variety of services? And that's what OTP does it in a unified way, so that no matter if you're designing a massively multi-user online game, a telecom switch, or a messaging application, your approach and your features will be the same, from system to system. They've solved the problem once in a way which works, and you then adapt those solutions to your particular domain.
Okay. So to get into a specific example, I want to talk about a specific example. So let's talk about deploying a software upgrade to an Erlang system. So I've heard this is a classic example of why Erlang can be useful, because upgrading an Erlang system without having downtime is one of the big benefits of the language. So how does OTP help with this upgrade process? Or how do you think about OTP in terms of this upgrade process?
Okay, so I'll break the question into two parts. One is the pure Erlang part, where you're able to upload a module in the runtime system. And by doing a fully qualified function call in a process, so basically by prefixing the module name to the function name, you do a check to make sure you're running the latest version of the code. And you can have at any one time two versions of the code in your virtual machine. And processes can run either the old one or the new one. By doing a fully qualified function call, you check and make sure that you're running the latest version of your code. If you're not, the pointer to the code base switches to the new version. And you do that by retaining your process state, by retaining variable values and your call stack and everything else associated with that particular process. So that's how the foundation works. Now, you can imagine, you've got very complex systems, handling huge finite state machines, protocol stacks, particular database schemas, and you need to upgrade from one version of your system to a new version. And, the upgrade might consist of changes in your protocol stack, changes in your messaging APIs, changes in your schema, changes in the process state. Just switching modules won't work anymore. You need to now also start coordinating your upgrades, possibly across distributed nodes. You need to upgrade your schema. You need to, have callback APIs which allow you to change your state. And most important, if your upgrade fails, you need to be able to revert back to the state, prior to the upgrade and then continue running the old version of the code. And so what OTP does, and that's actually in the SASL System Architecture Support Library application, is it provides a set of tools which will do all of the coordination, all of the suspension of the processes, all of the loading of the new modules, changing of the states, and then you're unsuspending the processes on your behalf. And it will all take a few microseconds up to a few milliseconds, depending how complex your system might be. In some cases, you might have to change your whole database schema, and that's going to take a little bit longer. But what you tend to do in those cases is that you change your database schema in the background and make sure that your upgraded code can handle both the new version and as well as the old version, and take it that way. So it is not, software upgrade in runtime, for complicated cases is not for the faint of heart, but it's the best way of doing it if you don't have any redundant hardware. And if you want to make sure that you can continue running your services without interruption, even during the upgrade itself. So what it does, it will give you the tools which you then integrate into your own tool chain. It will give you the APIs you'd go in and hook into.
Okay, so let's have a more general discussion. OTP also has generic behavior for just how processes should interact with each other. And this is obviously much more general. So processes get arranged into hierarchies with supervisors and worker processes. Could you give an example hierarchy to help explain how I would arrange supervisors and worker processes in a real-world system?
Absolutely. So think of a system which handles SMS votes. So you've got your, America's Got Talent or X Factor or Big Brother or whatever other trash TV your partner forces you to watch and vote via SMS on. And so in most of the cases, in the UK at least, a lot of the systems handling these SMSs are all Erlang based. And what you do is, as soon as an SMS is received, you create a new process which lives for as long as you're handling that particular SMS. So the way a supervision tree would look like in this case is you'd have your top-level supervisor, and then your top-level supervisor would start a process which would handle, say, the counter, which would handle all of the counting of the votes. So you go in and you vote for a particular user. Once your process figured out what this user is, you go into this process and you bump up that particular counter for that user. And you then have a second supervisor. So at the same level as the counter process, you'd have a second supervisor to which you hook in every single SMS which you start, you'd hook into this second supervisor, which would monitor it. And now what you can do in the supervisors are all generic code, is state the behavior and the dependencies among the process or among the siblings. So what you could state is that if, for example, the processes which parse SMS terminate more than 3 times a minute, the supervisor has a problem on its hands because there's a bug in its code and it can't handle them. So the supervisor could decide what to do. Does it restart all of the children? And so does it restart all of the SMSs which are being handled? Does it do nothing? So you're counting and you're dealing with millions of SMSs coming in a very short period of time. If you lose the odd SMS, it's perfectly allowed. Nothing's going to happen. And no one other than the person who sent the SMS is going to notice. So you're isolating the error in a particular process. On the other hand, if you start getting crashes or terminations in the process which is handling the counters, what you would do is the termination would reach a top-level supervisor, which would again probably go in and terminate the supervisor which is managing all of the SMSs. And you'd then restart the counter process with a fresh state, and you'd start a new supervisor, which would handle the SMSs, and then all of the new SMSs coming in would hopefully be hooked to the new supervisor and not have any issues. And
okay,
we keep on having issues. At that point, the top-level supervisor decides to escalate the issue, terminates himself, and lets whoever's monitoring the virtual machine to take action. It could be the rebooting of a machine or, calling in someone in operations to actually go in and inspect the problem visually and manually.
Yeah, okay. I love that example. That's really descriptive. So one of the strengths of the Erlang virtual machine is that there's a garbage collector per process. Explain how the per process garbage collector, how does this simplify the behavior of an overall Erlang system?
What a per process garbage collection does is it guarantees the soft real-time properties of the system. So unlike the
soft real-time, I'm sorry to interrupt, but what is soft real-time?
A soft real-time system is a system where you will guarantee that in most cases you will receive a response within a certain amount of time. But if that odd request exceeds that response time, nothing critical is going to happen. So an example is sending an SMS or a WhatsApp message. You're guaranteed, if the other user's online, that they'll receive the message within a few milliseconds. But if something happens with one odd message and it takes more than 1 second, to deliver, nothing's going to happen. Unlike, say, airbag control systems, where if you don't trigger the airbag within, I think it's something like 30 or 40 milliseconds, you're strawberry jam. I don't know if you're following the example. And that would be a hard real-time system. So,
Sure.
telecoms...
No, that makes sense.
Yeah, telecoms, historically are soft real-time systems. You pick up the phone, you'll 9 times out of 10, you'll hear the toot-toot within a few milliseconds. The odd time on New Year's Eve when you pick up the phone and everyone else is picking it up, and it takes half a second to hear that toot-toot, you won't react to it. What's important is that you get that toot-toot. And those are the properties which the Erlang virtual machine tries to retain, guaranteeing that you get a response within a certain amount of time. But if you don't, you will still get a response, but it might take a little bit longer. And that usually happens under extreme heavy load.
This episode of Software Engineering Daily is sponsored by Braintree Payments. Mobile app development can be complex, but integrating your payments no longer has to be complex. With Braintree, your business can accept nearly every type of payment from any device with just one integration. Learn more at braintreepayments.com/SEDaily. Braintree's API supports Android, iOS, JavaScript, and many other languages. The documentation for Braintree is clear and elegant, and if you're integrating payments into your app for the first time, you can call Braintree's customer service and get assistance with your integration. Don't get frustrated when you're trying to integrate payments and monetization into your app. Go to braintreepayments.com/SEDaily and monetize your app today. braintreepayments.com/SEDaily. Now let's get on with this episode of Software Engineering Daily. Thanks for listening. Okay, so back to the conversation about garbage collection. So how does the per process garbage collector help with that soft real time?
So what that does is you don't have a big stop-the-world garbage collector. Erlang processes don't share memory. So that means that you don't need to go in and reference data in other threads. The garbage collector gets triggered when a particular process needs more memory. And what it does, it tries to free up the memory required by that process. And as soon as it has freed up that memory, it will step back. And only after every few thousand garbage collections, it does what we call a full sweep, which is goes in and checks all of the data, to see if it can be freed or not.
So the garbage collection process is amortized across all these different processes.
It's amortized across all these different processes. It's triggered based on need, and it tries to be as unintrusive as possible. So using this approach, you don't have the problem where, all of the requests going through your system when the stop the world garbage collection triggers, it kicks in, which ends up, creating spikes in your latency. Your latency will be very constant in Erlang-based systems, yeah.
I think you pretty much touched on it there, but how would that contrast with another virtual machine like Java that would have that stop the world effect?
You'll have a quantile of requests. So maybe what could it be? You'll have maybe 1% of your requests, taking 10 times longer than all the other requests, just because those requests happen to take place when the garbage collector was triggered. And instead, with Erlang, it's very small, intensive bursts, many of them, but intensive. And so they won't affect you as much.
So I've seen systems where Erlang is used as the message passing layer between Java and JavaScript services. And they'll have, obviously Java and JavaScript have different garbage collectors than Erlang. So does it become very difficult to profile a system like this? Like, are there patterns to structuring these types of systems where you can get the bulk of the garbage in the Erlang VM or something, or do you just end up having to profile each different part of the overall system?
So Erlang is very commonly used as glue and proxies, to glue together different programming languages and also, connect different protocols together. It's excellent for it. Now, if you start combining your different technologies, what you need to do is profile your whole system end to end. You can't just go in and profile the Erlang part because It's a bit like trying to remove bottlenecks where you don't have bottlenecks. So what you do is profile your whole end-to-end system, and start creating load on one end, and then profile it that way. And based on those metrics, go in and narrow down where you basically need to optimize. I don't know if I've answered your question.
No, that's absolutely a good answer. So, two of the important parts of your book, Designing for Scalability in Erlang, they're about designing individual nodes and then designing how those nodes interact together. If I am designing an Erlang system, how should I think about these two different steps of the design process? The individual node design versus the design of how sets of nodes interact together?
That's a really good question. So the first step you need to do is start dividing your system into nodes. What functionality do you provide in the different nodes? And almost, try to visualize it as, creating a set of microservices which then interact with each other. And once you've divided the functionality, given the nodes a particular functionality, that will give you how they interact with each other almost, in a straightforward manner. You start adding more complexity when you start thinking of no single points of failure. So when you're dealing with multiple nodes, there are two things you're getting. You're getting scalability and reliability. And what we tend to say is you distribute for scale and replicate for availability. And that's where you start making your trade-offs, which we discussed earlier on. So in your design, you need to keep in mind, what happens if node A, which could be running your web servers, sends a request to node B, which is running the business logic of the system, and node B interacts with node C, which might be a database, storing and distributing your data. And you need to ask yourself, if node A sends a request to node B and node B doesn't respond, and it could not respond for a variety of reasons. It could be that it's terminated, that a software fault happened, that the network might be down. You might have actually, the computer itself crashed. So there might be a different variety of issues. What do? Do you forward the request to a copy of node A, so to a redundant copy? Do you have a redundant copy? And if you do, have you replicated the state across these nodes? So it starts getting into, this thinking of how do you go in and design, your whole distributed system. Most systems are fairly simple. You'll just have everything in one single node. And that's, typical, say, for proxies, which receive requests and then forward them on. Or, messaging platforms where, the nodes will be identical, but then you'd replicate some parts of the state across these nodes. So it's very, very application dependent, and it depends on the complexity of the application, which you're actually designing, how you end up doing it. Another question is, you need to ask yourself is, do you want to do capability-based deployment? Are you actually optimizing your hardware for, what your node does? If a node is a database, do you want fast disks, for example? Or if it's front-end nodes with, running web servers interfacing users, do you want some form of, you want to keep them stateless and have some form of logical or physical firewall, protecting them from the back-end nodes?
Yeah. So Erlang has the philosophy that's known as let it crash, which is like when a process has an error, the process should crash, and your system should be built with this in mind. So in your book, you write that this philosophy works particularly well when used with supervisor processes, and we already discussed this a little bit. So explain how this works in practice.
So to steal Steve Vinoski's quotes, Steve Vinoski's word, I think when you're dealing with, when we say let it crash in Erlang, we don't mean we ignore the errors. We just mean we handle them differently. And what we do is we handle them in a very generic way. So when a process has terminated, what we do is we discourage defensive programming. If you've come across a bug in your code or your state gets corrupt, trying to fix it in the code itself will rarely work, and it will actually add even more bugs to your system. Because if you knew what the bugs or how the state would get corrupted, it wouldn't get corrupted in the first place, or the bugs wouldn't be there. So what you do is, what we encourage users to do is let your process crash, and the supervisor then goes in and receives an exit signal. And upon receiving this exit signal, it's up to the supervisor to decide what to do. Does it restart the process? Maybe, if you're handling an SMS and parsing the SMS failed, chances that if you restart the process, the parsing is going to fail again. So you just drop the cases. In other cases, you might want to restart the process and retry. In a third case is you might want to terminate all of the processes which are part of the supervision tree, because the termination might have been caused by a dependency in some of the other processes in that subsection of the supervision tree. Or, the last strategy is go in and terminate all the processes started after this process which terminated. And this, points to a dependency in a particular direction in your supervision tree. And so what usually happens when you design your system is that the supervisor decides, what to do and how to manage it. And the supervisor could itself decide to terminate itself and let its top level supervisor then decide how to handle it. And this usually happens when you've received a certain number of terminations, abnormal terminations or crashes in a predefined number of seconds, and the supervisor reaches the conclusion that we probably have an error which I've not been able to handle with a restart. So by restarting it, I won't solve the problem. Let my supervisor deal with it. And the answer, the solution might be in a different supervision tree, part of the supervision tree, or it might be by restarting the node or actually even rebooting the machine. And so, all of the strategy is usually in the hands of the person architecting the system, and allows them to decide when they go in and design all of the design the system, design the processes and the dependencies among them.
So let's talk about shared state. Erlang systems can be built with the shared everything, shared some things, and also the shared nothing approach. As a systems designer, how should I explore these different areas of the spectrum?
Okay, so first of all, processes in Erlang there is no shared memory. They don't share any data. So it's a share nothing approach. So for two processes, to share data, they need to each have their own copy of the data. Distributed systems, the data and the state in your distributed systems, when you're dealing with, scalability and availability, that's when you need to decide what you go in and, what data you go in and distribute. And the whole sharing of your data and state across nodes will then give you different levels of scalability. So as an example, the share everything approach is the least scalable of them all, because in order to share all of the data, it will take up network, bandwidth, I/O, and CPU overhead. On that end of the scale, the most scalable approach is the share nothing, where you'll just have one copy of your data, and then if you lose that node, you lose that data. But that at the same time, is the most scalable of these solutions, as you're in effect, sharding on a per node basis.
So another spectrum of trade-offs that we can explore with these different types of systems is that of consistency versus availability. So how do we explore these different areas along the trade-off gradient of consistency versus availability in Erlang systems?
Okay, so if you look at the consistency spectrum, on one end of the spectrum, you've got strong consistency. And that means that you've got guarantees that the data will be the same on both nodes. And this is usually the most reliable system, but also the least available, because in order to guarantee this consistency, in case we get a network partition, we might have to take the system down. So by accepting the loss of occasional requests, you'll go in and start accepting an inconsistent view of your state or your data. And so that's where, and when you start handling an inconsistent view, this needs to be handled in the semantics of your system. So as an example, if you want an eventually consistent system, that would be a system where, the data eventually becomes consistent. The availability becomes, better, but the reliability, lowers down, as you don't know what version of the data you'll be getting. And on the other end of the spectrum, you'll have systems with no consistency at all. And even those are perfectly acceptable. Once again, it completely depends on the business logic of what you're trying to achieve. And, consistencies will also go in and affect the scalability, where, if you want your system to be strongly consistent, your scalability will suffer in that, you need to go in and duplicate your data, and you need to guarantee this duplication. And that means, many more requests, hoping that nothing goes wrong in that. Duplicating the data as soon as, you get timeouts or you get network partitions, you're left in a state of limbo where you're not sure if the data was duplicated or not. Eventual consistency, causal consistency, the less consistent you get, the more scalable your system becomes. And the most scalable of them all are those systems where you actually don't share any data. So, you've got copies of the data, but you're not sharing it. And it's in effect sharding of systems, and that's how you start getting massive scalability. And
go ahead.
What I'm saying is, this is nothing specific to Erlang itself. This is just generic distributed systems and trade-offs you've got to make between the two.
Certainly. Okay, so we had a show recently about Elixir, which is a language adds some complementary functionality to Erlang. What value does Elixir add to the Erlang ecosystem that we've been discussing?
A lot of value. I love what's happening right now with Elixir. What they've done is they've created a tool chain and a workflow which users who come from a Ruby background or a Java background feel familiar with. So what they've in effect done is they've reduced the perceived barrier to entry of using Erlang ODP, or if you're doing simpler things, the barrier to entry isn't high at all. They're both easy to learn. And so what they've done is they've opened the whole power of the Erlang virtual machine to a huge set of developers who until now have in effect been using tools which are not scalable for the job. So they've taken the power of Erlang and then extended it to make web development happy. And what's happening with Phoenix now is spectacular. We're seeing exponential adoption of Phoenix, where Ruby on Rails applications which are having scalability problems, and even Node.js applications which are having scalability problems, are slowly migrating to Phoenix, addressing all of these issues. We're hearing stories where previously they were running 10 instances of Ruby on Rails, all running at full capacity. They migrated to Phoenix, and they ended up running one Phoenix instance on the same hardware, running at the 10% CPU load. So incredible success stories, happening. And right now, as we're talking, Elixir Conf in Europe is ongoing, and and that's where a lot of these users are currently sharing their experiences. So, and I think Jose Valin all the other contributors have done a fantastic job at opening the doors of the power of Erlang to a much, much wider community.
So the computing industry has been exploring how to write language-level support for distributed systems for many years. Are there any other languages other than Erlang that you find compelling when it comes to distributed systems design?
So, to be honest, no. I'm still looking for languages which have integrated, so mainstream languages actually being used in the industry, not in academia, which have actually integrated the distribution model in the virtual machine itself or in the language semantics itself. Because, going back to what I was saying earlier, Erlang removes a lot of these accidental difficulties in, creating scalable, reliable systems. It doesn't do it by magic, but a lot of the things you'd struggle with conventional technologies are taken care of for you in Erlang. And so you end up focusing on the hard problems themselves. So I'm still, looking around and seeing there's a lot of research going on. And I think, there's a lot of things happening in that space, but I'm still waiting to see, wide adoption of the results of this research.
But so in other languages, there is distributed system support. Languages that are not inherently built for distributed systems,
yes,
they tend to have functionality bolted on to make these languages better suited to distributed systems. Why isn't this effective? Why doesn't this work?
So I'm here. I assume you're thinking in terms of pub sub interfaces, AMQP,
Yes. Sure.
And I wish Steve was on the show because I mentioned Corba as well. So it is effective. It does work. And if you look at massive scalability of Erlang systems, you'll also need to go beyond Erlang as well. Erlang will currently scale to about 70, 80 to 100 nodes. And then you need to start working your way around that. So that's no different. So Erlang's no different, to other conventional languages. But then again, you already have the luxury of being able to scale to 50 to 100 nodes before you need to start bolting on additional protocols and, additional layers to your system. And what that gives you is simplicity. So if you don't need to scale beyond that, you can do that in a very simplistic way without having to worry about Zookeeper, without having to worry about standardized protocols, pub sub interfaces, and so on. You do it completely transparently in your system. As sending, Erlang processes share data via message passing. Sending a message to a process on your local node or on a remote node, the syntax is exactly the same. So doing something right from the start with very little changes, you can take a program which was meant to run on a single node and then distribute it across a cluster of nodes. And so, this will work great until you start reaching, huge scale, Facebook scale or WhatsApp scale. And that's where you need to take it to the next level.
Okay, so I'd love to conclude by talking a little bit about the book. So give us an overview of what you go into in designing for scalability in Erlang, what we did not discuss today.
So I think the first part of the book, we focus on explaining behavior. So how you take processes and, give them a particular behavior. This behavior could be a generic client server. It could be a finite state machine, an event handler, a supervisor. And we explain how to package, create these supervision trees. So how to start thinking and reasoning in terms of supervision hierarchies, packaging them into standalone applications. So applications which then, which are loosely coupled from each other. You then take these loosely coupled applications and create a single node. And a single node, will provide a particular type of service. It could be a complete system, or it could be, part of the functionality a larger system provides. We then describe how to upgrade single nodes. And then from there, we describe how to take, multiple nodes and group them together, focusing on, scalability and focusing on availability. And we wrap up with something which is incredibly important. Erlang is renowned for, achieving 5 nines availability. So that's a few minutes of downtime per year at a fraction of the efforts of, conventional programming languages. But once again, you won't get your 5 nines out of the box or by magic. You need to be, very serious about your monitoring and your preemptive support. And you need to try to address faults, discover faults and address them before they escalate. And that's what the last chapter focuses on. So I think, so it's basically, the book is about taking a language and actually using it to build systems.
That sounds great. That's a great place to close off. Francesco, I want to thank you for coming on the show. This has been a fascinating conversation about Erlang.
Jeff, thanks so much for having me. It's been a pleasure.